morning, everybody. I am Mutlaq AlSubaie. I am a software engineer working with the world leading oil company, Saudi Aramco. Thank you. I would like to thank the organizers for this successful event, and I will discuss with you today the open source software impact in the oil industry. Hopefully I will not take that much of time. This is the outline. I'll begin the introduction about Saudi Aramco and the organization, brief introduction, just to tell you where the support for the petroleum applications in Saudi Aramco. I'll mention some of the impacts on the Saudi Aramco of the open source softwares. I'll mention some examples, and then I conclude my presentation. So let's give you a brief infrastructure about Saudi Aramco. Saudi Aramco is divided into 7 main business lines. I will not go through all of them, but I will mention the most important or the core business of Saudi Aramco, which is the exploration and producing business line. This business line is the objective of it is to explore and find the oil reserves in Saudi Arabia, and after finding them, try to drill and produce the oil from those reservoirs or fields. IT, let's talk about IT now. IT in the Saudi Aramco is divided into main sections. One of the IT departments is residing under the industrial relations business line, and its goal is to support all applications, human resource, finance, medical applications that serve the employees of the company. They support all business lines except the exploration and producing business line. The exploration and producing business line is so important that they have an IT for their applications, which is serving the petroleum engineering applications and geoscientists and production engineers. I'm working in the Expect Computer Center. This center is the IT of the exploration and producing business line. Their mission is to provide quality and cost-effective computing services to the exploration and producing business line. This includes hardware, software, and database technologies used to support the seismic data processing and the interpretation of those data, the reservoir description and simulation, the geologic modeling, the drilling and production operations, information management, and visualization. As you can see from the first sentence, here we have the word cost-effective computing services. Here we can see one of the impacts of the open source softwares. It's cost-effective, and we have a good open source softwares that we're going to mention later. The vision of ECC, the Expert Computer Center, is to be a recognized leader in providing world-class computing technology for the industry of oil and gas upstream operations, supported by a team of internationally certified professionals. These are some of the applications and libraries and standards we are using in the company or in the Expert Computer Center mainly. Of course, Linux and Red Hat is 2 main operating systems that we are using, but I didn't mention them because everybody is familiar with it. We are using Java as our development programming language, the Flex as the interface, the Virtual GL, I will mention it later, I will elaborate on it, the message passing interface, the Open MPI, the portable batch system, and the BlazeDS. I will go through each of them briefly. The Virtual GL. It's a system that gives any Unix or Linux remote display software the ability to run OpenGL applications with full 3D hardware acceleration. See, the Virtual GL, I will mention the previous days we have for that our engineers faced regarding the visualization tools and the simulation tools they used to maintain the fields and reservoirs of the oil. Previously, we had engineers having Linux or Unix machines as the local ones, and we have clusters and servers on the other side. When an engineer needs to simulate his field or his reservoir in order to manage the field and the production rates, he sends a request of an application. Let's hear an example, sim reservoir application. It's a simulation for the reservoir or the field for each engineer. The application resides in the server, and the engineer sends a request to launch the application. Once the application is launched, the remote server is manipulating the data and sends functions to the other local machine, the machine of the engineer, to execute these commands, graphical commands. Each line has its own command and square in a 3D format. So you can imagine how much data we are handling here. The components we have are the graphical processing unit on the local machine that handles the rendering. It receives the commands, graphical commands, and it renders them and executes them on the display. We have the network, and we have the memory and the CPU. As you can see here, we have a lot of data being handled in the network. It's too much information sent to one engineer. What if we have more than 10 or 20 engineers working at the same time? Also, there is a lot of load on the GPU, on the local machine. The CPU and memory, we don't have to worry about it because it's a server, so it's supposed to handle this amount of data. What we used is the virtual GL application. The virtual GL helped us. This is the local, this is the remote server. We send the same request for the launching of the application. And rather than sending the data itself, the virtual GL executes the functional commands on the server itself and takes the end result, sends the snapshots of the end result of the reservoir in 3D format to the local machine. You may be wondering what is the effectiveness in this method. As you can see, we saved a lot of GPUs. If we have too many engineers, we don't have to buy them, everyone his own machine with his own GPU, which is cost, which is really not cheap. And the bandwidth of the network is not overloaded because it doesn't handle that much of data that were functional before. So we had all three parts, the GPU, the memory, and the CPU in the remote server. That saved us a lot of money and a lot of time supporting the GPUs. Rather than having 100 engineers with 100 expensive GPUs, we had only one GPU or two on the servers, and every engineer executes the functional commands, and it's being rendered in the GPU of the server and sends it to that engineer. The message passing interface. It's an interface that is used in the clusters to pass messages between each other. The reasons for using MPI. Standardization. MPI is the only message passing library which can be considered as a standard. It supports virtually all high-performance computing platforms. Practically now, it has replaced all previous message passing libraries. The portability and the availability. The portable batch system. To elaborate more on this, it's a primary task to allocate computational tasks, that is the batch jobs, among the available computing resources. We have our geophysicists who are receiving the huge amount of seismic data after scanning a certain area or certain field. They want to see how much oil we got under the ground, or if there's oil or not under the ground. So you can imagine how many data points we have, and each data point, how many data we have to process. Each geoscientist executes some jobs and commands to scan the data, highlight some for the data point where the oil reserves reside, and we have a lot of them. So the portable batch system, it allocates the resources needed for that engineer. If we have like certain number of clusters, each cluster having certain number of CPUs, and each CPU having that number of nodes, it allocates the amount of resources needed for executing that job. For example, if an engineer executes a job that takes a day, so it goes, the portable batching system goes to a certain node that will be busy, that will not be busy for a certain day, and